In the last video, we saw how information flows through neural networks, and we discovered that that's basically through the process of forward propagation. And now we have to talk about back propagation. In fact, we started talking about back propagation a lot before we mentioned forward propagation in the last video. Of course, both concepts always work together. So in this video, we say back propagation finally explained. What exactly is that? In the last video, I also pointed it out a couple of times that forward propagation is for making predictions, while backward propagation is for learning. That is, fine-tuning parameters, fine-tuning the weights and things like that for better predictions like that. Okay, so backward propagation finally explained. Of course, we know it has a lot of applications. Back propagation is a learning algorithm that made modern artificial intelligence possible because the whole essence of modern artificial intelligence is that you make predictions and they are not as accurate as you expect, and then you can fine-tune things and keep getting better predictions until you finally land on the result that is desirable. And that is so with if there was only forward, in fact, what you have always had in mathematics and in life was forward propagation. Yeah, we probably did have a machine way of making things correct themselves. So humans had to do all the corrections. But now with artificial intelligence, so you make predictions, you don't get what you want. There's backward propagation to fine-tune parameters, make better predictions, and keep going until we get the best of what we need to get. So backward propagation is the learning algorithm that made modern artificial intelligence possible. So every successful deep learning model relies on back propagation to improve its predictions by learning from its mistakes, basically. So forward propagation for predictions, backward propagation for improved predictions by the process called learning. Learning from mistakes, learning from the error, from the loss, the error between reality and the prediction. So back propagation is the engine behind computer vision, image classification, object detection, face recognition, natural language processing, speech recognition, speech machine translation, recommendation systems, medical diagnosis, autonomous vehicles, robotics, reinforcement learning, scientific machine learning, and of course large language models, LLMs. Without backpropagation, neural networks would make predictions but would never improve. So you just have the forward part without the backward part, which doesn't improve anything. So backpropagation is often regarded as the single most important algorithm in deep learning because it provides an efficient way to compute how every parameter in a neural network should change in order to reduce prediction errors. So you see backpropagation, it has both things like gradient descent and uh, of course, in gradient descent, you have gradient, right? So you have that idea of gradient, chain rule and everything put together in this one thing. So if you're going to say one important keyword in the whole idea of artificial intelligence, it is back propagation. So it is often regarded as the single most important algorithm in deep learning because it provides an efficient way to compute how every parameter in a neural network should change in order to reduce prediction errors. So our learning objectives, by the end of this lesson, you should be able to explain why neural networks need back propagation. I mean, I've said that in a way. Then understand how gradient flow enables learning. We've seen that in previous videos. Derive gradients using the chain rule. We've also done that before, but we just want to explain in some depth. So explain the mathematics behind weight updates and compute gradients manually. Implement backpropagation from scratch in Python. And understand vanishing and exploding gradients, which we've talked about a whole lot. Explain why every modern deep learning model depends on backpropagation. From previous videos, we saw the idea of vanishing and exploding gradients due to the fact that you have different layers of gradients being computed, and they are put together by the process of chain rule, and as a result of that you have a propagation of you have maybe a sharp decline in the gradients such that everything becomes slow, and or learning stops altogether, or you have it exploding so high that it doesn't make sense. Now, why learning is difficult, right? Suppose you are learning to play basketball. You throw the ball toward the basket. If you miss, someone tells you too far left, right? Then you adjust and you throw again. Now they say a little too high. So you have to keep working about making sure you don't go too far left and you don't go too high or too low and everything. And again, you adjust. So with every instruction, you keep adjusting, right? So after many attempts, your throws become increasingly accurate because each mistake provides information about how to improve. So neural networks learn in exactly the same way. A neural network begins with random weights. Since the weights are random, its predictions are usually poor, right? So initial weights are random. I think we made it. There was a video I made on that. The fact that you start with randomness, but you have to go on a guided search, no longer random search, right? Start randomly and then go guidedly, so to speak. So the learning process follows four simple steps. First of all, you make a prediction. Secondly, measure how wrong the prediction is. Thirdly, determine which weights caused the error. Fourthly, adjust those weights. And then the challenge lies in step three, where you determine which weights caused the error. That's where the challenge is. So you have to then suppose a neural network contains 10 weights or 1,000 weights or 1 million weights or 100 billion weights. How can we determine exactly how much each weight contributed to the final error? And then backpropagation solves this problem efficiently by computing gradients. So instead of guessing which parameters should change, it computes the precise contribution of every weight to the prediction error. This allows neural networks to improve systematically rather than randomly. That is why you start randomly and you now go systematically predicting the right results. So learning can be pretty difficult, but backpropagation solves the problem. Now, forward propagation review, that is what the last video was about. Before a neural network can learn, it must first make a prediction. So before we do back propagation, there must have been a forward propagation, which leads to prediction. So before a neural network can learn, it must first make a prediction. So this process is called forward propagation. Now consider a single neuron receiving two inputs. You have inputs X1 and X2 and weights W1, W2, and bias B. I mean, we have said that so much that by now that should have been etched into your memory. So the neuron first computes a weighted sum, Z equals W1 X1 plus W2 X2 plus B. So the weighted sum is then passed through an activation function, A equals sigma of Z. So where sigma of Z is equal to 1 all over 1 plus e raised power minus Z. Finally, you then have y cap equals A. And so y cap equals A is the network's prediction. At this stage, the neural network has not learned anything, right? Because now, so you compute the weighted sum, you pass it through an activation function where theta of Z can now be like sigmoid function or whatever you choose. We saw different types of activation functions like the rectified linear unit activation function, that's a ReLU, which takes the maximum of 0 and whatever number you have, and then you have sigmoid function, which is this one, and then you have tanh function too. So finally you then have y cap, which is equal to A, which is the network's final prediction. Okay, so at this stage, the neural network has not learned anything. This is just a prediction here, A. And for most likely, A is not good enough, a prediction, but it is a good point to start, a good way to start. So at this stage, this is just your first prediction. No learning has happened yet. So it has simply performed a sequence of mathematical operations that transform the input into an output, basically. So learning begins only after we compare this prediction with the correct answer, right? Learning begins only after we compare this prediction with the correct answer. So now, talking about measuring error now, a prediction by itself tells us nothing about whether the network is performing well. So we therefore compare the prediction with the true target value. So suppose the target y equals 1 and prediction is y cap equals 0.73. So the target is 1, like we know 1 is the correct answer and the prediction is 0.73. So it's a bit close, but not close enough. It could have been 0.99 or something. So it could even be 1, right? So the prediction is close but not perfect. So to measure the difference, we use a loss function. So one of the simplest loss functions is the mean squared error, which takes the mean value of the. So you take the difference in the target and the prediction, square it, and divide by the number of predictions you have. So in this case, the quantity L now is called the loss, which is a measure of the difference in the predicted value and the actual, or what you can call the target value. So the loss represents the cost of making an incorrect prediction. So several observations are important. Small loss means accurate predictions. Large loss means inaccurate predictions. A loss of 0 means perfect prediction. That means your prediction is exactly what the target is. So the objective of learning is therefore straightforward. We minimize the loss, right? We want to minimize the loss. That is the essence of learning. I mean, we've talked about, I think we had a whole video on loss already, right, on the loss function. So everything that happens during backpropagation is aimed at reducing this single quantity. So our goal now is to make sure the gap between the target and the prediction is small enough. That's basically what backpropagation is about. Now that it makes us talk about the learning problem. So suppose a neural network contains only one weight, for instance. If the prediction is poor, it is easy to adjust the single parameter, easily. However, real neural networks are much larger. For example, a small neural network may contain thousands of weights. Everything we've been doing so far in this place where you see just two or three weights, these are just for you to understand the mathematics going on behind the scenes, right? But in reality, you have thousands of weights. So a convolutional neural network may contain millions of weights, in fact. So large language models contains billions of parameters, which are like weights. So if the network makes an incorrect prediction, we must answer the following question: which weight caused the mistake? And you have billions of parameters. What do you do? So more importantly, we also have to check by how much should each weight change so that you can get a better prediction. So changing every weight by the same amount is ineffective because different weights contribute differently to the final prediction. So some weights have a very large influence on the output, others have almost no influence. So therefore, every parameter requires its own correction, and then backpropagation computes these corrections efficiently by calculating how sensitive the loss is to each weight. So this sensitivity is called the gradient, and that is where the idea of gradient descent comes into the matter. So why gradients matter then? We've talked about this a couple of times. So in previous videos, that is, so a gradient measures how much the loss changes when one parameter changes slightly. So if a weight should change, how does it make the loss smaller or bigger? That's the idea of gradient. So mathematically, the LDW represents the rate at which the loss changes with respect to the weight. So the gradient provides two critical pieces of information. First of all, it tells us about direction. If, for instance, the LDW, the rate of change of the loss with respect to the weight, is greater than zero, increasing this in so if this happens, increasing the weight. So if you increase the weight, it will increase the loss also, right? Therefore, the weight should decrease. So in this case, if the LDW is greater than zero, is positive, that is. So if you increase the weight, the loss will also increase. So the error will increase. On the other hand, if the LDW is less than zero, if it is negative, if the weight is negative, increasing the weight will decrease the loss. So it means in that case, the weight should increase. So you're going to have different weights. Some of them, the rate of change of the loss with them will be greater than zero. So such weights should be reduced. And then you are going to have some weights. The LDW for them will be negative. So such weights should be increased. So it is in that balancing that you then get a better prediction. So we then talk about the idea of magnitude. So a large gradient means the weight has a strong influence on the loss, right? So whether it's negative or positive, but and that determines whether you should reduce the weight or increase it, depending on what we've just seen now. So a small gradient means changing the weight has little effect. So small gradients don't change the weight. Don't worry too much about changing the weight so much. So once the gradients have been computed, each weight is updated using the gradient descent. Each weight, imagine 1 billion weights is updated automatically using this simple, and that's why the whole idea of AI is a simple one, but because of the tons of data you have, it becomes very serious, very intimidating and overwhelming, in fact. So the new W is equal to the OW minus eta multiplied by the LDW, where eta is the learning rate. So this simple equation is the fundamental learning rule used throughout deep learning. Very simple thing, and that is what drives everything. So every training iteration follows the same cycle. So you have so every training iteration follows the same cycle. You have forward propagation, you compute the loss, you compute gradients using back propagation, you update the weights. Forward propagation is that first prediction you make, that prediction you make, and then so between that prediction and the reality, you compute the loss. What's the difference like? Then the next thing, you compute the gradient using back propagation to see how each weight affects the loss, how each weight either increases the loss or decreases it, and then you now decide, okay, which one should you increase, which one should you reduce. So then you update the weights like that, then you repeat until the loss becomes sufficiently small. So in the next section, this introduces the mathematical tool that makes backpropagation possible. So backpropagation is made possible due to what is known as the chain rule, which we had actually seen before now in a video like that. So I think that's a video titled "The Tiny Rule that the tiny rule that makes AI learn or something like that. So backpropagation is built upon one of the most important ideas in calculus. So you see, very simple concepts here and there come together to form the gigantic AI we now talk about. So backpropagation is built upon one of the most important ideas in calculus, the chain rule. So the chain rule allows us to compute the derivative of a function that depends on another function. So it helps us to compute the derivative of a function that depends on another function. So function of a function. Chain rule helps us to find the derivative of functions of functions. So for example, suppose the loss depends on the prediction, and the prediction depends on the activation, and the activation depends on the weighted sum, and the weighted sum depends on the weights. So this relationship can be written as this: L of A of Z, and Z of W. So this weight does not affect the loss directly. All right. Instead, the weights affect the weighted sum. So weight affects weighted sum. The weighted sum affects the activation, and then the activation affects the prediction. Finally, the prediction determines the loss. So the chain rule simply tells us that change in loss with respect to weight is simply change in loss with respect to activation multiply by changing activation with respect to weighted sum, multiply by changing weighted sum with respect to the weight easily. Notice that the derivative is broken into smaller pieces, and each piece is easy to compute. And the sweet thing is that dA can cancel dA, dZ can cancel dZ. So at the end of the day, you still have your LDW like that. So it's more like you have a chain connecting everything together so you can get the overall result. So multiplying these pieces together gives a complete gradient. So this idea is extremely powerful because a deep neural network is simply a long chain of mathematical operations. So instead of deriving one enormous equation, backpropagation computes one local derivative at a time and multiplies them together. So this makes learning efficient even for networks containing millions or billions of parameters like that. So we then have backpropagation, right? Backpropagation is the algorithm that computes how every weight in a neural network contributed to the prediction error. All right. So backpropagation is that algorithm that computes how every weight in the neural network contributed to the prediction error. And you say why backpropagation is powerful. So its primary objective is to calculate the gradient of the loss function with respect to every trainable parameter. Rather than guessing how the weights should change, backpropagation uses calculus to determine the exact direction and magnitude of each update. So the algorithm proceeds backwards through the network. So the sequence is you have the output layer, you have the loss function, you have the activation function, you have the weighted sum, and then you have the weights. So at each layer, the error information is propagated backward using the chain rule. So this backward movement of information gives the algorithm its name, right? So you have backward propagation, which is the same thing as backward propagation of errors. So the output layer computes its gradients first. Those gradients are then passed back to the previous hidden layer. Each hidden layer computes its own gradients and passes them further backward. Eventually, every weight in the network receive its own gradients. So these gradients are then used by gradient descent to update the parameters, and then backward propagation therefore transform prediction errors into useful learning signals. Just like I showed in the previous video, right? Imagine you have your output layer right here. You have output layer. So you have the output layer like this. So in between the output layer, you then have hidden layers, which ends up in an, oh, sorry, this is input layer. Input layer. You have the input layer here, and then you have the output layer here. So all of these are hidden layers, and they can be so many. You can have thousands of hidden layers, depending on the situation you're dealing with. So, so you pass your X and W here with the bias. So, and that is, so you go through the whole process of, computing the weighted sum and activate and getting the activation function. And then here now, the first activation A1 comes here with another set of weights. So let's say this is X not W not B not if you like. And then you have another weight and you have another bias. So this is done, and you get, so what you get out of all this is A1, right? So out of all this, you now get an A2 out, which goes in here. You have A2, you have W, and another weight, another bias, and then you get A3 out of this, which goes here. So you have A3 and you have W3 bias 3, and that those are all hidden layers. Finally, you get an A4 out of this. So the A4 comes in here with another with 4 bias 4 done done properly, and then you get an output. So the output here is the prediction you get. So here the input is X and the weight and all of these things like that. So that's the idea. So the deal now is you have this is forward propagation right here. This is forward propagation. This is forward propagation. But then after the first input is made, so the difference between this input and the target, the result you're expecting, the difference is computed. And then once the difference is computed, then the every weight that you've seen before will now be the difference in them results to the loss, right? So the L, the W tells us how the loss changes depending on the weight, and that whole process takes place through a process of backward propagation. Okay, well, I think I've actually gone forward. Okay, well, man, that's first layer, right? So in that case now, so all the weights you had here, you now have new, okay, the X remains the X, right? But the weight now, you have new weight and probably new bias or something. And then, so this can now be fed now into the process again. And that's what keeps going until you get the kind of predictions you want. So this is the process of back propagation, like that. Okay, so that you then have so we have all of that happening. So backpropagation therefore transforms prediction errors into useful learning signals. So um okay, like we know, each hidden layer computes its own gradients and passes them back further backward. Eventually, every weight in the network receives its own gradient. These gradients are then used by gradient descent to update the parameters. Propagation therefore transforms prediction errors into useful learning signals. And then we have the idea of the gradient flow, which we also saw before in the previous video. So one of the most important ideas in deep learning is gradient flow. So gradient flow refers to the movement of gradient information from the output layer back toward the input layer. So that's the idea of backpropagation. So during the forward pass, information flows in one direction. So you have input layer to hidden layer to hidden layer to hidden layer, or whatever hidden layer you have up to the outputs. But then during backward propagation, the information flows in the opposite direction from right to left. So left to right for forward propagation, but left to right for forward propagation, right to left for backward propagation. So forward propagation leads to prediction. Backward propagation leads to learning, fine-tuning of parameters for better predictions. So during propagation, information flows in the opposite direction. So after the you get a prediction. So the loss is computed. That is passed to the output layer, and then passed to the hidden layer, passed to the hidden layer, and back to the input layer, where gradients would have been computed and everything, and better weights, better parameters are then obtained for the next iteration, and it goes forward. So you have forward, backward, and it keeps going until you get your desired result. So every neuron receives an error signal indicating how much it's contributed to the final prediction error, and each neuron then computes gradients for its own parameters before passing the remaining gradient backward. This process continues until every trainable parameter has received an update signal. So good gradient flow is essential because it allows all layers to learn simultaneously. So if gradients become too small, each layer learns extremely slowly, and if gradient become too large, weight updates become unstable. So you don't want too slow, you don't want gradient to be too small so that the learning doesn't stop altogether or becomes too slow. If gradient become too large, weight updates become unstable. You want to maintain that balance. So maintaining healthy gradient flow is therefore one of the central challenges in training deep neural networks. And then that takes us to the idea of the learning mechanism. How does learning take place? Basically, the idea of back propagation, the whole learning mechanism happens in back propagation. So back propagation does not learn by memorizing examples, no. Instead, it gradually improves the network through repeated correction of its mistakes. The complete learning cycle consists of the following steps. You have step one, perform the forward propagation, where you compute y cap first prediction using the current weights. Then the loss is computed. In step two, you have L is 1 over 2 y minus y cap squared. So if you have many para predictions, right? So you have to take a summation of all of this. Then it's like if you have many predictions coming out, then step three, you run the backpropagation, which where you compute the LDW for every weight. Then in step four, you update every parameter using this simple gradient descent algorithm. New weight is equal to old weight minus learning rate multiplied by the gradient of the loss, which is the rate of change of loss with the weight. Then in step five, then we have to repeat. You rinse and repeat. So the updated weights produce a new prediction and a new loss is computed, new gradients are calculated, the weights are updated again. This learning cycle is repeated hundreds, thousands, or even millions of times. So over time, the loss decreases, the predictions become more accurate, and the neural network gradually learns the underlying patterns in the data like that. So then every propagation for a single neuron, back propagation for a single neuron, for instance, consider a neuron with input x is 2, weight is 0.5, bias is 0. So no bias. So target is y equals 1. So what do? You compute the weighted sum where you have z equals wx plus b. So 0.5 times 2 plus 0. So you have 1 there. Then you can apply the segment function or any other one you feel like applying. If you apply ReLU to this, the answer is 1. If you apply segment function, you get a equals 1 over 1 plus e raised to minus z. So a is equal to 1 over 1 plus e raised to minus 1, which is 0.7311. So since y cap is now a, so the prediction is y cap, which is 0.733. But the target, if you remember, is 1. So we compute the loss between what we have got and 1. So if you compute the loss now, use the mean squared error. You have L is 1 over 2y minus y cap squared, right? So substituting, you have L is half into 1 because the target is 1. The predicted value is 0.7311. So you square that, you have L to be 0.0362. So the network made a small error, but it is not yet perfect. So the error is small, but it's not, I mean, it can be better. So the next step is to determine how the weight should change. That is where the learning thing happens. So then we talk about computing the gradient. So we now compute the gradient using the chain rule. So the LDW, for instance, is the LDA plus D multiplied by the ADZ multiplied by the ZDW. So if you differentiate the loss, okay, so where's the formula for the loss now? um so half y minus y cap, and we know that our y cap here is actually a, right? So we have the LDW. So if the LDA, rather, the LDA. So the predict y cap is a, right? So y minus a. So if we differentiate this, we end up getting a minus y. So the LDA is a minus y. So if you substitute a, which is 0.7311 that we got, so we have that, and y is also 1. So it means that the LDA is minus 0.2689. A we got, y we know as a target, and then differentiate the sigmoid function. So the sigmoid function is actually a equals 1 over 1 plus e raised by minus z. So if you differentiate that, we end up getting, okay, let's even do that. So we have the sigma function a to be 1 over 1 plus e raised by minus z. So that means a is equal to 1 plus e raised by minus z raised by minus 1. So the a, the z, right, is equal to this function of a function. To differentiate this, bring down the power, then differentiate inside with respect to z. So differentiate 1, that's 0. Differentiate this, that's minus e raised by minus z there. Then you have 1 plus e raised by minus z raised by minus 2 now. Reduce the power by 1. So the z now is equal to, this is e raised by minus z here into 1 plus e raised by minus z raised by minus 2. So that is the z equals e raised by minus z all over 1 plus e raised by minus z raised power 2 now. Raised power 2. So how can we split this up? So we already know this is 1 over 1 plus e raised by minus z. So dA dz is equal to, so we can have e raised by minus z all over 1 plus e raised by minus z multiplied by, so this is squared now, all over 1 over 1 plus e raised by minus z, like this. So this is square now. So this whole thing is a, right? And then I think this is 1 minus a. A in the sense that So when I mean A, this is A like this. So this is A here. And I think this is 1 minus A. Okay, let's just do the maths. Like 1 over 1 over 1 plus e raised power minus z. So that's an aside. This is 1 over 1. So the LCM is 1 plus e raised power minus z. So 1 here, that's 1 plus e raised power minus z minus 1. So this cancels out. Yeah. So yeah, we are good. So this is 1 minus. So we see that the A dz, the A dz here is equal to 1 minus A. This expression is 1 minus A, and this is A. So we have dA dz is equal to A into 1 minus A into 1 minus A, like this. So that's what we have right there. So that's exactly what we have here. So where is that now? So okay, the loss has been computed. So we compute this, differentiate the segment function, dA dz, that's A into 1 minus A. So therefore, dA dz now is A, we already know is 0.733, 0.7311, 1 minus A, 1 minus 0.7311, that's 0.1966. Then step 3 now, differentiate the weighted sum, Z is Wx plus V. So since we have the Z dW is simply, so the ZW here will simply be X, and we know X is 2. That's what was given originally. We know X to be 2, yeah, like this. So X is equal to 2. So multiply all derivatives together. So we have dLdW now. So the loss is simply minus 0.1058. So this gradient tells us both the direction and magnitude of the weight update. Since the gradient is negative, increasing the weight will reduce the loss, right? So if you increase the weight, the loss will be reduced. So gradient descent therefore increases the weight during the next update step, because you have a negative gradient like that. So that's the process. I mean, that's easy to handle because you have just very few data points, but in the real setting, you have tons of that. So you need super machines for that. So after computing the gradient, the neural network is finally ready to learn. So the gradient descent update rule is then new gradient is equal to old gradient minus learning rate times the gradient. New weight rather is equal to old weight minus learning rate times the gradient, where W old is the current weight, N is the learning rate, dLdW is the gradient. So suppose the current weight now is 0.5, and then the learning rate is eta 0.1. So the gradient dLdW is minus 0.1058 that we computed from here. Okay, so substituting these values into the update equation, we have 0.5 minus 0.1 multiplied by minus 0.1058. So since subtracting a negative number is equivalent to addition, we then have 0.51058. So the weight is increased slightly. So this is exactly what the negative gradient suggested, right? So if we perform another forward propagation using the updated weight, the prediction will move closer to the target, resulting in a smaller loss. This illustrates the fundamental idea of learning. That's the learning mechanism basically. Now using the whole, so starting from forward to backward altogether. So if you can then compute the error, you calculate the gradients. So this illustrates the fundamental idea of learning. Compute error, calculate the gradients, update the weights, and repeat. So every deep learning model follows this process millions or even billions of times during training. So Python implementation of what we have just done, right? So the following Python program performs one complete iteration of forward propagation, backward propagation, and weight updating for a single neuron, just like the one we had up there. So you have the input and the target. So the input is x equals 2, and the target is 1. So the initial parameter 0.5 and b is 0. Learning rate is taken to be 0.1. For forward propagation, you have z equals wx plus b. So the activation function is 1 over 1 plus e raised power minus z. And then the loss is computed at 0.5 times y minus a raised power 2, like that. So then you have that's half y minus a, like that. So print the prediction is 8, and the loss, you have that. Then for back propagation, you have the LD, that's a minus y. The a dz is a into a, y minus a. Dz dw is x. So the gradient then is the LDA multiplied by the a dz times dz dw. Then you print the gradient and use the gradient descent to update. And in one step, you get that result right there. So the prediction is 0.7311, just like what we saw up there, and we did it manually. Then you have the loss. The initial loss is 0.036164, blah blah. And then you have the gradient, which is minus 0.1058, just exactly what we got. And the updated weight is 0.51. So normally this should happen over and over again until we get the final result. So this is what the whole code looks like right here. Okay, so training the neuron repeatedly. Learning does not occur after a single weight update for sure. So instead, the network repeatedly applies forward propagation, backward propagation, and gradient descent until the loss becomes very small. This following program trains the neuron for 100 iterations. So if you want to do the same thing, the same thing for 100 iterations, the same input, the same weight, the same prediction, the same target, right? And the same weight and everything. But now we have 100 epochs. So, and that's what we have for epoch in range 100. Forward propagation, you have that. The activation. So you keep doing that. You also do have the loss, and you keep doing that until you do it 100 times. So finally, after everything is done, we print the final weight. So, we started with a weight of 0.5 for W, right? So the final weight becomes 0.9964. The initial prediction was 0.7311. The final prediction is 0.879. And then the final loss is now 0.0072. So way smaller than, the loss here was 0.03. So now you have two zeros before the 7. So that's 0.007. So that's how that happens. So during training, you see that the prediction gradually approaches the target, right? So you see our target was 0. It was 1, right? So now the 0.99 is to one decimal place it's 1, to two decimal places it is 1, to three decimal places, yeah, it is at three decimal place that it is 0.996. So it's pretty close now. So it means if we even continue, we can even get 1. In fact, let me do this and maybe make it 200 iterations. So I run this. So you see it has, oh, it is even already overshooting. So that also tells us something. So maybe 150 will do the job, right? 150. Okay. Yeah. So around 120 we should be good to get that one. Yeah, something like this. So, but you see already 100 iterations is already giving us 0.99 stuff. Yeah. So the prediction gradually approaches the target during training. The loss decreases. The gradient becomes smaller. So you can see the grade. Okay, the gradient isn't here now. Then the weight converges toward an optimal value. So this repeated optimization process is called training. So when you say you are training a model, this is what exactly is happening. So whether training a tiny neural network or a large language model containing billions of parameters, the learning process follows the same fundamental cycle. And then we have the idea of gradient checking. So backpropagation relies on mathematical derivatives, like we've seen. So if even one derivative is implemented incorrectly, the entire learning algorithm may fail. So to verify that gradients are correct, researchers often perform gradient checking. So instead of computing the derivative analytically, we estimate it numerically using finite differences. So the numerical approximation is the LW, which is approximately L of W plus H minus L of W minus H all over 2H. I mean, under numerical analysis, I've done this kind of thing a lot. So where H is a very small number, so it's a little increment. So this procedure is simple, slightly because you can the procedure is simple. You slightly increase the weight, that's W, then compute the new loss, slightly decrease the weight, compute the new loss, estimate the gradients using the finite. So this is a slight increase in the weight, this is a slight decrease in the weight. Then you estimate the gradients using the finite difference formula, which is this now. So if the numerical gradient closely matches the analytical gradients computed by backpropagation, then the implementation is likely correct. So gradient checking is extremely useful when developing new neural network architectures because it helps identify implementation errors before large-scale training begins. Although gradient checking is computationally expensive and therefore rarely used during actual training, it remains one of the most important debugging techniques in deep learning. So gradient checking is a nice debugging technique. So then we have the idea of automatic differentiation because we're talking about tons of derivatives here. So modern deep learning libraries automatically compute gradients. So instead of manually deriving every derivative, software performs backpropagation automatically. And we have popular frameworks include PyTorch, TensorFlow, JAX, MXNet, MindSpore. For example, in PyTorch, so you have things like loss.backward, which computes every gradient in the computational graph. Similarly, you have TensorFlow uses tf.gradient tape to calculate derivatives automatically. And then you have automatic differentiation which works by recording every mathematical operation performed during the forward pass. These operations form a computational graph. During the backward pass, the graph is traversed in reverse order, and the chain rule is applied repeatedly to compute all gradients. Although software now performs these calculations automatically, the underlying mathematics remains exactly the same, like I've explained before. Every call to loss.backward is fundamentally executing the backpropagation algorithm developed from the chain rule. So when you see this loss.backward in PyTorch, you should know that what is happening there is backpropagation based using the idea of chain rule. Then we talk about vanishing gradients, like talked about this before in previous videos. So one of the greatest challenges in deep learning is the vanishing gradient problem. So during backpropagation, gradients are multiplied repeatedly as they travel backward through many layers. So suppose the gradient is repeatedly multiplied by 0.2. So after several layers, you have 0.0016, which becomes pretty small. So the gradient rapidly approaches zero. As a result, early layers receive almost no learning signal. So weight updates become extremely small. Learning becomes very slow. Deep networks may stop improving altogether. So this phenomenon is called the vanishing gradient problem, and several important techniques have been developed to overcome it. So that's why we have things like ReLU activation. So unlike the segment function, the ReLU activation preserves stronger gradients for positive inputs. So that way it's just discriminating between whether the value you have is zero or zero or something more than zero, right? Then you can also have better weight initialization. Carefully choosing the initial weights helps maintain healthy gradient magnitudes during training. And then there's batch normalization. So batch normalization stabilizes activations, improving gradient flow throughout the network. And then you have residual connections. Residual networks like REST-nets introduce shortcut connections that allow gradient to flow more easily through very deep networks. And these innovations made it possible to successfully train neural networks containing hundreds of even thousands of layers like that. And then apart from vanishing gradient problem, we also have the exploding gradient problem. So of course, the vanishing gradient problem is your gradient approaching zero, making learning really slow or even shutting down learning altogether. So the opposite of vanishing gradients is the exploding gradient problem. So instead of becoming smaller, gradients become extremely large as they propagate backward through the network. Suppose the gradient is repeatedly multiplied by 3, for instance. After only a few layers, after 5 layers, you have 243. Imagine you now have 10,000 layers. That's a lot. So the gradient grows rapidly. So large gradient produce excessively large weight updates. So instead of moving gradually toward the minimum loss, the optimization process begins to overshoot. I mean, we saw that in a previous video where we see that if you choose more like the idea of learning rates, so you have this oscillation jumping around. So training becomes unstable. The loss may oscillate widely or even become undefined. So typical symptoms include sudden jumps in the loss function, extremely large parameter values, numerical overflow, training that completely diverges. Several techniques help prevent exploding gradients, like gradient clipping. So you can clip the gradient to a particular value. So if it exceeds that value, you don't take it. So gradient clipping limits the maximum size of the gradient before updating the weight. For example, G clip can be the maximum between minus C and the minimum of G and C. So where G is the original gradient and C is the predefined threshold. So proper weight initialization then becomes like proper weight initialization is another way to take care of the exploding gradient problem. So initializing weights with appropriate distributions reduces the likelihood of unstable gradient growth. Examples include Xavier initialization and He initialization. Then we also have batch normalization, like what we had the other talked about under the vanishing gradient problem. So batch normalization stabilizes the distribution of activations, helping gradients remain within a reasonable range. So, and then you have residual connections. Residual networks provide shortcut paths that improve gradient flow and reduce instability in very deep networks. So modern deep learning systems combine these techniques to ensure that gradients remain stable throughout training like that. So thankfully, we have solutions to the vanishing gradient problem and the exploding gradient problem. So let's talk about application of backpropagation, which we've talked about several times. So backpropagation is the universal learning algorithm of deep learning. So the universal learning algorithm for deep learning, that is backpropagation. So regardless of the architecture, so you see, instead of backpropagation, you have gradient descent. Inside backpropagation, you also have chain rule. So And putting all of this together, you have the whole idea of learning. So regardless of the architecture, nearly every modern neural network learns by computing gradients through back propagation, regardless of the architecture. So computer vision for computer vision, we have applications of back propagation in image classification, object detection, face recognition, medical image analysis, image segmentation. And we have popular architectures like convolutional neural networks and vision transformers. So that's for computer vision. So these are some popular architectures there. Then for natural language processing, backpropagation enables machines to understand and generate human language. So applications include machine translation, text classification, sentiment analysis, question answering, text summarization, with popular architectures like recurrent neural networks, RNNs, long short-term memory networks, LSTMs, gated recurrent units, GRUs, and transformers also. I mean, my first love in artificial intelligence is actually machine learning, and the next love I have in artificial intelligence is about natural language processing, which I've not started exploring, but I mean, I've started, dancing around it a little bit. So, but I know it's a matter of time. Now, for speech recognition, now deep neural networks trained with back propagation can convert speech into text with remarkable accuracy. So, you have applications including voice assistants, dictation systems, speaker identification. All right, and then we have reinforcement learning. Many reinforcement learning algorithms use back propagation to improve policies and value functions. So, examples include deep Q networks, DQNs, actor critic methods, and policy gradient methods. Then, of course, we have it in scientific machine learning also. Backpropagation is widely used in climate modeling, drug discovery, computational biology, medical diagnosis, physics-informed neural networks, and neural ordinary differential equations like that. So I get to play around scientific machine learning a little bit because I try to use it for biological, ecological, and epidemiological problems. Then we have generative artificial intelligence. Modern generative models are trained using backpropagation. Examples include generative adversarial networks, variational autoencoders, diffusion models, large language models. Today, virtually every major breakthrough in artificial intelligence relies on backpropagation. So, another thing to consider why backpropagation changed artificial intelligence permanently, right? Before the development of backpropagation, training neural networks with many layers was extremely difficult. Researchers knew that deeper neural networks could represent more complex functions, but there was no practical way to determine how each weight contributed to the final prediction error. Without an efficient learning algorithm, increasing the depth of a network simply increased the number of unknown parameters. So backpropagation solved this problem. So backpropagation was a lifesaver, right? By applying the chain rule systematically, it computes the gradient of the loss with respect to every trainable parameter in a single backward pass, just a single pass. Even we have tons of gradients to compute. So instead of estimating gradients independent for each weight, backpropagation reuses intermediate computations. So this dramatically reduces computational cost. As a result, deep neural networks became trainable, optimization became efficient, learning became scalable, and modern deep learning became possible. Today, backpropagation powers virtually every state-of-the-art neural network. So whether training a small classifier or a large language model with billions of parameters, the underlying learning algorithm remains the same. So for this reason, backpropagation is widely regarded as one of the most important algorithms ever developed in artificial intelligence. So, some summary and key takeaways. Backpropagation is the mathematical engine that enables neural networks to learn from their mistakes. So the learning process can be summarized as follows. Step one, perform forward propagation to generate predictions. Step two, measure prediction error using a loss function. Step three, apply the chain rule to compute the gradient of the loss with respect to every trainable parameter. Then step four, allow gradients to flow backward through the network during back propagation. Then step five, update every weight using gradient descent. That's new weight is equal to old weight minus the learning rate times the gradient. Then step six, repeat this cycle many times until the loss becomes sufficiently small. So key takeaways now. So neural networks learn by minimizing a loss function. Okay. Then gradients measure how sensitive the loss is to each parameter. Then the chain rule makes efficient gradient computation possible. Then backpropagation propagates error information backward through the network. Gradient descent uses this gradient to update the weights. Healthy gradient flow is essential for successful deep learning. Vanishing and exploding gradients are major challenges in deep networks. Modern techniques such as the rectified linear unit, ReLU, batch normalization, residual connections, and gradient clipping improve gradient flow. Automatic differentiation in modern deep learning frameworks is an implementation of backpropagation. Every major deep learning architecture, including CNNs, RNNs, LSTMs, transformers, GANs, diffusion models, PINNs, and large language models, depends on backpropagation for learning. So, final thought: forward propagation allows a neural network to make predictions. Back propagation teaches it how to improve those predictions. All right. So forward propagation allows the neural network to make predictions. Backward propagation teaches it how to improve those predictions. And that is what we call learning. So together, these two algorithms form the foundation of modern deep learning and have transformed artificial intelligence into one of the most powerful technologies of the 21st century. So some practice problems. In this case, I won't solve any problems because I think this has taken so much time already. And I think the concepts are pretty straightforward because we've done it a couple of times, right? So I'll just flash the problems and hope you take care of them. So, but if you really need help with any, you can let me know in the comment section, either on Facebook or on YouTube, and probably I'll make a separate video to take care of that. So this is problem one right here. You have the inputs, you have the weights, you have the bias. You want to compute the weighted sum. That's pretty easy. That's just WX1, W1x1, W2x2, W3x3 plus B. So that's 0.6 times 2, 0.8 times minus 1, 0, minus 0.3 times 4 plus 0.5, and you get your Z. Then now you have questions 2 to 2 and 3. So use the weighted sum. Z is minus 0.75. Compute the sigmoid activation. So you just throw this into a sigmoid function and you get your result. Then binary cross entropy loss. So here you want to compute the loss here. Use the binary cross entropy loss to compute the loss based on these values now. So then you have for interpreting the gradient, a neural network computes the LDW is 2.35. So explain whether the weight should increase or decrease. Of course, because the LDW is 2.35, which is greater than 0, so it means that increasing the weight will increase the loss. So in that case, it means that you should reduce the weight. So why this update reduces the loss? Okay, of course, this update will reduce the loss for sure. But when you decrease the weight, the loss will also decrease. So in that case, it will decrease the loss, right? So if effect of the learning rate, so a weight has value this and gradient that, compute the update with using, of course, the smaller learning rate learns slower than 0.2. So this, of course, the two of them, this is smaller than this. This is moderate. So this will be slow but steady. But this will move a bit faster and still convert to the results. Most likely. So compute the derivative of ReLU. So the ReLU activation function f of z is max OZ. Compute df dz for each value. Z is minus 4, Z is 0, and all of that. Then so then you have the chain rule. So suppose the chain rule is all this. So I mean, we can do chain rule easily with this. Just dLdW will simply be dLdu multiplied by du dv multiplied by dv dw, and you get your answer. I think that's one I was supposed to solve, except for the fact that the time is fast spent. Identify gradient flow. Consider the network this. List the order in which gradients are computed during backpropagation. This is very close to the last problem I solved in the last video. So you want to check that out. Then number of gradient calculations. A neural network contains 15 neuron layers in a hidden. Yeah, let me just flash all of this for you. And then so this here you have 9 to 11 all showing. 9 to 11. Then now you have 12 to 16 all showing. And then 16 to 20 here. All right, so on this note, thank you very much for listening. Thank you so much. Let me know how helpful this is for you. If there's something else you want me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, what exactly are you waiting for? Why not go ahead right now, subscribe to this channel and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you special privileges special privileges that you find out when you click on join. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.